just a quick reminder on everybody, please turn off your microphone so that we can focus on the speech of Ingo Thon. So thank you very much.
From time to time, you also hear interesting things from the background, especially company secrets. So,
yes, yeah, I got
so, thank you for the warm welcoming words. So my name is Ingo Thon, and you should actually be able to see me as well. So give me one more second, sorry for that one, to enable my camera. So hopefully you can see me now as well. No, okay. So my name is Ingo Thon, and I'm working in Siemens factory automation, as just explained. So when it comes to factory and manufacturing, a lot of people, when talking about AI, have something like this in mind, where a robot is automatically handling objects, moving them in a manufacturing area, pulling them out, handling them completely autonomously, and hopefully in an intelligent manner. So the interesting thing is, when I'm talking about AI, I typically do not do anything with robots. Actually, I do not even like them. So when you see this application where the robot is picking up the new material for the next manufacturing process, there's no intelligence inside. A lot of people have thought about, yeah, the robot can actually handle the machine autonomously. Nevertheless, the guy who built this machinery thought, okay, instead of having the robot arm opening the doors, I can actually put up here 2 pneumatic cylinders to open the door. And actually also the points where the robot picked up these blocks, so the robot is not identifying where a block is standing with a camera or something. It's just pre-programmed. There's a grid on the table. Somebody has align the blocks on the table, and everything is automatically. So there's no intelligence in this thing. When I think about intelligence and automation, and maybe even this domain, there would be actually an application for intelligence where, if you think about it, the robot is picking up that piece, placing it over here, and picking up the next piece and placing it again in the machine. However, there's a lot potential for optimization if the robot would not move the entire way back, but basically take one of the non-manufactured block while the machine is still operating, place it here on the corner, pick up the old material once it's finished, place it again on the corner, put the new one in the machine, and then putting the old one back, the ready one back in line. So that would be a real intelligent system, but this is very, very far away from our current state. And most of our applications are sadly a little bit more boring, nevertheless challenging enough and interesting enough, and most importantly, as I will show in the remainder of this talk, will generate a lot of value for our customer. So what is factory automation in general? So I guess most people have heard the story of the Industrial Revolution with Henry Ford, where the first industrial revolution was actually a little bit earlier with the automatic weaving machinery, which got a program. Actually, it was the first computer. Side note, the first programmer in the entire world was a woman, to the big surprise of many people, Ada Lovelace. And she basically invented a language as well, how to program these machineries. A little later than Henry Ford, mass automation of the manufacturing line. And since 1980, we have more and more digitalization and more complex infrastructure in the production of cars, whatever you choose, food and beverage, everything. And since 2010, there's the so-called Industry 4.0, the fourth industrial revolution, where digitalization, IT, and all these technologies we know from our computers in daily life take a larger part in the automation of the industries. So the business unit I'm working for is called Factory Automation, and the big question is, what are we actually producing? So in factory automation, we are building products to build a plant. So this might be a PLC. A PLC is something for controlling a plant. So switching things on and off, measuring values, and so on. We are producing HMI. HMI stands for human-machine interface, which communicates between the control and the human, but also, for example, controls for motors, which are produced by Siemens. And these equipments are used then for various different applications, and actually an extreme wide area of applications. So the most obvious one is electrical manufacturing, which you see at the bottom left. This is our own plant in Amberg, where we build our own product. So this is electronics manufacturing. But then I'm currently sitting in Munich, so I need to have two applications from Munich. Also beer breweries, for example, are controlled using these equipment, and tunnels. So in the beer brewery, it's still somewhat understandable why people are using industrial equipment to do the manufacturing automation. So this is basically open and closing ventiles, starting the cleaning process of the valves and so on and so forth, measuring pressures that nothing is overshooting. The tunnel is a little bit more surprising, but there the application is the control of the ventilation system, for example. And the reason why people use equipment from industrial automation is very simple. We have so-called high availability systems. They will never ever crash. So what you know from your desktop computer, a blue screen will hopefully not happen, or actually it's almost guaranteed that this will not happen. So this equipment is continuing to operate whatever happens in the world. Also, if something still goes wrong, so one PLC, the CPU, the controller is crashing, you can plug out the old one, plug in a new one, and the line, or the tunnel in that case, will continue operating like it was before. No rebooting or anything in the way you know it from your computer. So this is the current world with this equipment. The big question is what is coming next? And that's what I'm going to talk about in the next minutes, basically how AI and actually IT technology will influence our automation world. So a traditional automation system is set up in a very strict fashion. So the people from the automation world, they are not IT people like me. They are coming from a field which is called operations technology, and they typically studied or learned industrial engineering. And they have a complete different mindset from a computer scientist. And that's one of my biggest challenge in my daily life, that I'm not talking to a person which has the same mindset that I have. So one big thing I needed to learn when I started this work in the industrial automation world is to put myself into the shoes of the person in front of me, which is not a computer scientist, but often an electrical engineer or somebody who has no technical knowledge at all and is just interested in how to brew your next beer. And this, and together with the requirement that whatever happens, the production is still operating and can never fail, has fixed to a certain paradigm how to build up such a system. And this is called the automation pyramid, which is basically defining the OT level. And this is, it starts down at the process where the thing actually is happening. Then on top of the process, you have the inputs and outputs. And the inputs and outputs is basically the instrumentation of the different sensors and the actors, so valves, for example, and just connecting these. And then on the next level, you have something which is called as SPS. So I recall, or a PLC, SPS is, I think, the German Speicherprogrammierbare Steuerung, yeah. So SPS is the German term. There should be PLC, a programmable logic controller. This is actually the thing which decides to turn something on, turn something off, yeah, where all the magic happens, I would say. And on top of that, you have the Scada system, which is basically the big control screens you'll quite often see in a plant which is interacting with the humans in an operating room. And then on top of that, you have the management level, where at least I don't care so much about. And whatever we are doing in this world has the goal to improve on 4 aspects. And actually, if we are in the AI world, honest to ourselves, actually everything which AI does should follow these goals, which is basically we need to improve the time to market of our product. We need to increase the flexibility of our product. We need to improve the quality of our product, or we need to improve the efficiency of our product. So efficiency might actually be the time somebody needs to perform a certain task. And these are the things we are trying to optimize with AI as well. And now the interesting thing starts that the IT people like me are coming to the shop floor, and we are now having strange ideas. And one of those strange ideas is I'm doing machine learning. So if you look at the textbook, what machine learning means, it's basically a system which improves with experience. So you have a system which needs to have experience to improve. That's actually a definition which to a certain extent can also hold for the term AI. So where does the experience come from? It's basically data. And where does the data come? It comes from your production process. However, if you erect an industrial plant, you typically start to set everything up, then you program your plant, and then you expect it to operate. Maybe it's a few fixes, but if the AI guy says, yeah, I cannot program anything or train anything, or however you want to call it, before the plant is there, this is already strange. And then I said, okay, AI, machine learning is to improve the system with experience. So I'm actually expecting that the production system is improving the more time I have. This can sometimes cause a lot of confusion or unhappiness, because the automation people are more like, yeah, we build up the plant, we program it, and then it operates for 30 years. And it operates every day the same way it has operated before. And then I retrain my machine learning model and something changes. So theoretically, you need to check again, like you did on the first day of the plant, whether it's still operating correctly. So that is the second big challenge we have as machine learning people, that we are needing data, we need to iterate over and over again. And especially if our system is a critical part of the production process, then it basically needs somebody needs to take over on the first few days the functionality of AI. And that's, again, a very big challenge for us, which is hard to solve. And that's something we as AI machine learning people need to be able to communicate with the people actually owning the plant, operating the plant, that they need to come a little bit closer to us and accept that these things take time. Nevertheless, we from Siemens are not the first people which think about this, and the trend that IT and OT world will cross more and more is something which everybody has, or a lot of people which look into this world have now accepted. And they are mainly looking at the automation pyramid and see that the top level, which I ignored before because actually it looks already very much like IT, will be more and more like the standard IT technology, where you have things like cloud, REST services, and so on. But the expectation is that in the long run, this cloud services will also go to the lower level. So instead of having a controller close to your factory plant, people are assuming that the controller is moving to the cloud, operating from there. For me, this sounds not so much like a good idea, because if I lose my connection to the cloud, there will be no control anymore and the production stops. But that's at least what consulting people are quite often telling. My personal perspective is a little bit differently. My assumption is that all this AI functionality, as long as it is possible, will sit on the side of the automation system. So you have the classical automation pyramid, which operates like before. So you have your input outputs, you have your control and so on. And then you have an IT functionality which sits on the side and augment the existing system. So this is commonly called in the IT world an edge device. So a device which bridges the gap between the existing OT level and the IT level, which is the cloud. And the cool thing for me as a computer scientist is the edge protects me for screwing something up with the automation world. And then I can still use my IT technology like Docker containers to connect to my factory and start to do my AI stuff. Nevertheless, what we always need to keep in mind, and I added this here, is that we are crossing two worlds. So we are bringing still together the world of IT and OT, and I mentioned it before, those people are electrical engineers, so they are expecting that I speak in their language. You can see that actually from the way we are providing them to program our PLCs, controllers. So here you see the quote-unquote programming languages, which are these function blocks where they put signals close to the function block. And the reason for that is, as I said before, the guys which are programming these devices are electrical engineers. And if you look at the background, so all these PLCs were replacing somewhere in the 60s relays. And the relays were defined by all these control planes you see in the background. So basically the modern the programming languages of these PLCs are adopting these functionalities. And this is basically the way I need to communicate with people. And then to re-emphasize the other point, here I have my iterative world, and the automation people are typically have something which is called a V model. That's the way how we programmed in the computer sciences, I would say, until the 2000s, where you start to define your requirements from the system to the subsystem to the component level, and then you implement that bottom up. And as computer scientists, we switched that to this iterative process. As I said, for machine learning, this is extremely crucial because we cannot do it otherwise. Nevertheless, the OT people still require this way of building up a system that way for a very good reason. So a piece of software, if it's not working, you can easily replace it. Once you involve heavy metal in your building up your plant and you decide you need to change the entire mechanics of your production plant, this will be extremely costly. So we need to cross these two worlds. However, if we are able to bridge these two worlds, we can actually start to do cool stuff. And that's the part I'm talking about now. What are we actually doing with AI in the shop floor? So the most prominent case, which has been discussed since Industry 4.0, so I would say since around 2010 or even earlier, is the use case of predictive maintenance. So in the automation world, we have a lot of equipment and the equipment might fail. So at some point you have some wear and tear on the production machinery, and if it you would like to replace it before it fails, and on the other hand, you would like to delay the maintenance as long as possible. So we need to have something which tells us, okay, this piece of equipment will live for an additional 5 days, and afterwards you need to do the maintenance. The second use case, which has been discussed quite often, is the one of quality inspection, where you, for example, would like to inspect the welding seam. So you have a robot welding something and you check afterwards the welding process, and the system should tell you, okay, this welding seam is okay or not okay, so that somebody can remove the car or whatever or fix it in the production such that nothing not correctly manufactured will end up on the streets or wherever the equipment is running later on. Then also a very nice use case is the one of state prediction. So here you see a conveyor belt from beer breweries, and if you look closely, between the beer bottles there is a gap. And the idea of this conveyor belt is that the beer bottles are pushing each other. So if you have a gap, one beer bottle might fall over, and then it breaks and blocks the entire production. So the idea here is to use a camera to identify that there is a gap and take countermeasures. The countermeasure in that case would be stop or slow down the next machine, so the gap will close again because of the bottles pushing, and then you go the next machine again on full speed. And then, so I talked about quality inspection on vision. Also, if we would like to do quality inspection on time series data, so if you have, for example, a welding Zange, if you have a welding system, you have the electrical current and the voltage of the welding process, and you would like to actually do the prediction that the welding seam is not okay, based on this data, for the easy reason, while it's welding, you cannot see anything because there's a bright light due to the welding, and you could, with the electrical data, you can actually do this, predict this failure while the process is running, and then you can do much more likely a fixing of the problem. I started to talk about machines parts lifetime prediction, and mentioned what we would like to do there is to predict that the machine equipment fails in, let's say, 5 days, or you basically would like to predict the remaining time of life for this machinery. And this sounds for an AI guy like me like a regression task. So in machine learning, we call regression when you try to predict a numerical value based on some input features. So input features would be the process parameters, and the numerical value is the number of days the equipment will still survive till the maintenance. And actually, we did a use case that was actually pre-FA times for myself. That was times where I supported wind power in a consulting project, Siemens Wind Power, now called Gamesa, and they had the goal to predict when the power generation, the generator of the wind turbine will fail. And the reason why this predictive maintenance task is extremely important is you see the ship, and if you would like to do a service for a wind turbine which is offshore, you have two choices. You either go there by ship or by helicopter. Helicopter is a big problem because of weather. So if you have too much wind, you can obviously not go onto the platform. If you have too little wind, actually it's also a big problem because then you have turbulences. So ideally you have a certain amount of wind which stabilizes you going down. So if you see videos of these guys, it looks pretty cool. They go from the helicopter in a 45 degrees angle down to the wind turbine because they hope for a steady wind, which gives them secure going down. So bottom line is you can reach the turbine maybe 70 days of the year, and Siemens is actually providing service contracts which guarantees the operator of the wind turbine that the wind turbine is operating 90% of the year. So basically you should not miss a maintenance because otherwise it will be extremely costly. And the specific problem we looked at was connected to this generator you see in here. And it's basically a big copper coil which is insulated by resin. And the resin might melt, and then the copper coil is building short circuits. And these short circuits will then lead to Lichtbogen, so electrical energy crossing, which causes the copper to melt, and then the generator is broken. And hopefully you will detect that before it happens. And I said before, we are using regression here. So we are trying to predict how many days a wind turbine will survive. The interesting thing is we never see a wind turbine dying because most of the time they are doing maintenance before it happens. And even if that happens, that we see a wind turbine die, we quite often don't know when this happens. So we don't know the exact day when it was dying. So we have very lousy data. So I illustrated in that figure here. So a lot of wind turbines are living longer than we see it. A lot of wind turbines, or some wind turbines, we see actually the day where it dies, and a lot of wind turbines we have days where this breaks down. And this is called in statistics censoring. And if I now apply the standard machine learning technology, which is regression, to this kind of data, I will get a lousy model. And funny, I've seen a lot of people failing on exactly this use case for exactly this reason, where a statistics guy is only saying, obviously it's not working. And so basically the big challenge is that a lot of machine learning people, I would say, ignore the statistics world way too much than they should. And we didn't ignore it, so we used a statistics model, which is called the Cox Survival Model. It comes actually from healthcare. And there the idea of the model is you would like to predict, given the treatment, how many days the person is still surviving. So there it's to model the value of a certain medicine. We turned that a little bit around. We didn't measure the value, but the impact or damage by certain operations conditions. And actually the assumption, I mentioned the resin before, is that the resin is melting or is damaged once the turbine has reached a too high temperature. So we're building a model which was able to predict the number of days, the Cox model, the turbine is surviving on sensor data. We were also investigating how much the impact of this temperature to the wind turbine is. And what you can see here is that wind turbines that we can predict that's basically the predictive accuracy of the model is the vertical axis here, that the predictive accuracy of this model increases a lot once we model the temperature, and also that we were able to prove that the temperature is shortening the lifetime of the wind turbine. The other thing is that we were able to prove that the service of Siemens is also prolonging the lifetime of the turbine, which made our customers very happy. So message here is also for machine learning people, statistics is still an extremely valuable tool. And actually these models are now merging. So that's a paper which was published in 2017, I think. It's called Deep Cox model. So in machine learning, the current trend is to call everything deep and make everything deep. Cox model is the statistics model which we used as well. So these two models are crossing, and using the right technology, you can actually do the predictive maintenance task very well for the wind turbines. So this brings me now to the other use case which I mentioned before, the quality inspection. And here we didn't look at welding seams, so we looked at our own product. So what you see up here for time in the image is one of our components. It's a so-called base module, which you use to connect the electric with the wires, so to say. And you see here 4 images, and the lower half of the image is actually the bottom of the top of the part, and then you see the upper part of the image where you see a mirror showing you the side of the piece. So the people did not put up their 3 cameras to investigate the thing from top, left, and right, but basically put a mirror to the left and to the right. I cut off the bottom part, so you now see the top and the left of the piece. And the goal here is to predict whether a failure happened or not. And as you can obviously see, you can see nothing, or maybe someone has found where the piece is broken. I also indicated it. This is this area over here where the clamp is not directly connected. And then a lot of people are telling me, yeah, this is a standard classification task. So I had before the regression task where you try to predict numbers with machine learning. And this is on the first side, it's a task which is called classification. In classification, we try to separate different classes. So this would be good and bad in that case. The tricky part is now, if you look at the image, it has an extreme high resolution. So we are talking here about, I think it's 1920 pixel in the vertical axis. And this high resolution causes a lot of problems with the machine learning models. So in machine learning, we traditionally have 228 pixels. And this extreme high resolution gives us a lot of trouble. And what comes on top here is, and that's the other big challenge we have in these use cases typically, is we only have a very few broken pieces, which is good because it means our production is reliable. But our internal customer asked us that we should solve this use case by only seeing 10 broken pieces. Luckily, there's a solution to this. So what we did is something which is called meta learning. It's a few-shot learning technique, few-shot learning, because we only have a few examples there. And I will only try to describe what happens there on a very high level. So the basic idea of meta learning is to train your neural network, your AI function, like a little child learns. A little child, when it learns, it basically puts up increasingly complex tasks. So I have a 2-year-old son, so I can see this kind of on a daily basis. So the first thing he tries is to maybe stack 2 blocks, then he stacks to build higher towers. After he figured out how to build up towers, he builds up complex structures. So he puts up to himself an increasing complex task. And the same we are doing in meta learning. We are changing the task for the machine learning. So we start with a very simple task, which is in our case, or not a simple task, we start with the first task, which is, for example, detecting this clamp being a failure. And then the model has a short time to train on a few images, and then we switch the task. So we might predict that this white connector here is missing. We also have images on that. And then it learns a few iterations, and then we again switch the task for the machine learning model. So we take the next failure. Or we producing here not only this single kind of base module, we are producing several kinds of base modules. So we are trying to train the model to tell apart the different base models we are having. Or we are trying to distinguish different kinds of failures. So we are constantly changing the goal for the guy. Humans typically hate that, or not the guy, the machine learning model. Humans typically hate that, but actually what happens in the machine learning models, it starts to learn how to learn new tasks. So we are not training the model on a specific task, but we are training it on learning new tasks. And by using this technology, we can actually build a model which can learn new failures on only 10 images. For the people which are more interested in the algorithm behind, it's called Reptile. It has been published. It's not by us, but we used it only. But the paper has been published, and it's actually an extremely cool read from my perspective. But then the next challenge comes. So we have now built a machine learning model, and the big question is, how do we get it onto the shop floor? So I mentioned before, we have this traditional OT world where the people are electrical engineers, and quite some electrical engineers don't like PCs. And if I would like to deploy a machine learning model, I typically say something, yeah, you use a Docker container, you put it on your IPC, industrial PC, and then you connect the camera to the IPC. And then at least at one car manufacturer, the guys were like, no, not one more IPC. We don't like these things. They have a high maintenance effort. They are costly. We need to install Windows updates. Stay away with that. Luckily, we have an answer for that. As Siemens, we have the so-called TMNPU, and actually it's a device which you can connect to your production, your control system, and you can deploy your neural network directly on that device. And based on this, we can then train the model as we did it before, and then run it directly in the production without any PC, without any IT technology left anymore. Actually, the IT technology is still there, but inside of the box. And the OT people, the electrical engineers, don't have to touch that. And that's, for them, a pretty cool thing. So this is it on the visual quality inspection. However, so I mentioned it before that we have the machine parts lifetime prediction use case, which is there already since a very long time, and actually for a good reason, because it's something which is good solvable. So if you would like to do quality inspection, like on the quality I had here before on the image, typically you need to track the data of the entire lifetime of a product. So you need to track the product over its entire lifespan or entire production span, and this generates a lot of data. And if we look at predictive maintenance, like for the wind turbine, you only need to have the data of the one machine and not what happened to the piece which has been produced before and after. Visual inspection is here a little bit different, because there we really try to find the failure for the single piece. So coming back to the predictive maintenance use case, I hope it's not the case that a colleague of mine has showed it here in the ZOLLHOF event already. It's again something from the manufacturing line where actually the images were taken, I just have shown. And this little board you see, so here you see the green piece, it's a PCB board, is actually later on ending up in these base modules. The problem is, however, the PCB board, they are made of epoxy tarts. If you mill that like it happens here, so you see not only the part, this board does not contain the part only for one base module, but in total 16 base modules, and they are separated using the spindle here. And the problem is the epoxy tarts, which is milled away, is highly aggressive. It is going in the spindle, and then it will break the spindle. So the people would like to predict whether the spindle is failing, and the idea is very simple. So if the motor is blocking, what happens is that the revolution speed is going down and the current is going up. And when this happens, you know, you have maybe one more day where you can operate, and then you need to replace it. And you would like to do the replacement in this use case during the day, because in the night shift, the person who can replace the spindle is not there, and then the line is not operating for an entire night, or worst case for an entire weekend. And so if you do something like that, you basically build a model which takes the current and predicts the revolution speed, so you get a somewhat linear model, and then the data is scattering around this line, and you then measure how many sigmas, so standard deviations, it is away from this compared to normal. And here we have, for example, an outlier, which is a very abnormal behavior. So compared to the current, the revolution speed is very low, and that basically means the machine breaks. It's not the data from this use case, but from another use case. The realization of this use case is a little bit more complicated. So the guys which implemented that use case did not only take a single point, but used multiple points in history, but this is not that easily to plot on that chart here. Nevertheless, the AI guys then say, yeah, we need to think here about the use case. So we need to think what is the current, that the current influences the revolution. This is complicated, and also I learned, yeah, there comes the model to rescue, which is a so-called autoencoder. An autoencoder just takes the data of the input, so you basically feed into the autoencoder all the measurements you do on the machinery. You try to predict the these values again with your model, and the trick with the autoencoder is that you see that the model is here a little bit tighter, so on a very abstract level, it basically compresses your data. So if you compress something and uncompress it, it's some kind of, you need to find some kind of representation which predicts the states of your machinery. And if you are able to predict your model very accurately, you found a good representation. If you now train your data with, if you train your model with data which does not contain any failures, the model will be able to learn all the how to compress and uncompress the data of normal operation. But once you feed in the data of bad operation, it will start to compress the data. And once you start to uncompress the data, something completely different comes out. So you only need to measure, okay, when does the input and the output data of this model differ? And then you know, okay, something is going wrong. This is not typical operations data. The annoying part here is, yes, you can use a model like this, and most AI guys like to do that. Actually, I'm guilty here. But the tricky part is these models typically find all anomalies in the production process. And that leads again to a big challenge if you use AI in production. We measure a lot of things for very good reasons in production processes. And if you measure a lot of things, nothing is ever normal. So you will basically never ever see the same behavior of a factory twice, more or less. For a machine learning person and statistics person, this is pretty obvious. It's called the curse of dimensionality. If you have a lot of dimensions in your data, it basically has a lot of states. So a professor of mine illustrated it a long time by the following analogy. So if you have a pizza and you like or you hate crust, and if your pizza is 1D and the crust is something like 10%, so you have 20% crust. If you hopefully learned in school that if you go to a 3-dimensional pizza, the crust is much more than 10%. Because in dimension, it's basically squared. If you go to 3 dimension, the crust is even more. And if you go to an extreme high space, so here we have n dimensions on that image, you have a hyperdimensional pizza, so to say. And if you have this hyperdimensional pizza, your entire pizza consists of crust. And this is the analogy which basically leads to the fact that if you have a high dimensional input space, so if you measure too much, you have a high dimensional space and nothing will ever be normal. So your entire autoencoder will typically say, okay, this data is not normal, this data is not normal, this data is not normal, this data is not normal. And from my personal experience, the one time where actually you saw data which indicates the failure which you would like to predict, it says, okay, this case, everything is fine. So a little bit of warning, if you look into this kind of anomaly detection, it's a lot of engineering. You need to understand your process and don't throw your favorite machine learning model onto that one. But the idea is really to use your background knowledge and try to predict, use a model which is much more valuable. And then I brought a last use case, which I like to mention that because it kind of contradicts what I said before, but it helps us a lot of, it helps me to illustrate some more important aspects here with the challenges. So in this, again, it's the same manufacturing line in Amberg. At the end of the line, there's an X-ray. And the X-ray is scanning the entire PCB board, whether it's okay or not okay. So here you see the line. And at the end, here's the X-ray. And the problem is that the X-ray is the bottleneck of the entire production. So if you would not have the X-ray here, the production would be roughly twice as productive. Nevertheless, you need to check your boards whether they are okay. Otherwise, you build a piece of equipment which is not working correctly. This is what you want to avoid. So the idea with AI was here to collect all the data to predict then in the end whether the board will be checked by the X-ray as being okay or a failure. And if you can predict that this board is guaranteed to be okay, it can bypass the X-ray. So the only thing which you need to do is to predict the guaranteed okay boards, and then you can put them out. A little bit tricky part, I was not involved in that case personally, but on similar cases, a lot of people don't think, from my perspective, long enough about the KPI, so the key performance indicator, what you would like to achieve. So traditionally, a machine learning model is trained for accuracy. So you would like to have your model predicting whether the board is okay or not okay, as accurate as possible. Here, however, we need to be careful because we would like to predict whether it needs to have an X-ray or does not have to have an X-ray. This is what is called as machine learning measure precision. So you would like to have so you would like to optimize that whenever the system says this board is okay, it is guaranteed to be okay. And you need to use there a different KPI, and then you run in the funny situation that, as before, most of the machine learning algorithms are invented to optimize accuracy, and then you use a different matrix. So often you need to fiddle a lot around with the entire training of your, or the entire training pipeline until it does what you hope it to do. And then the other thing why I showed it, so if you would like to, here we need to have the entire parameters for this one single PCB board, and you need to measure here an unimaginable number of 40K production parameters. So in predictive maintenance, people are typically talking about 100 production parameters. If we would like to predict the quality of a PCB board, we need to capture something like 40,000 parameters, which is a massive amount of data. And you need to be able to deal with that data and then use that for prediction. So this brings me to the end. I showed you a lot of use cases. I hope I illustrated quite a few challenges, and also a little bit, I like to talk the presentation limitation of machine learning. because I highlighted a lot of limitations when you're just following the machine learning textbook and AI textbooks. You always need to look to the left and to the right, which is statistics and also other knowledge, and not use your favorite machine learning model and push your data through the machine learning model and hope that it works, because quite often this will not be the case. And now I'm happy to answer your question, and while I answer your question, I hope I can actually enable the camera.
All right. Thank you, Ingo, so much for your efforts and your time. It was very, very interesting, so we highly appreciate it. Before we start the question section, I would like to structure the whole thing a little bit. As I already wrote in the link, in the email where you get the registration link, I already mentioned that if you have a question, you're welcome to raise your hand virtually, like with a small icon you can see in the bar in the middle of the screen of Microsoft Teams. And yes, I would just call you, and then it's a little bit structured, and that's easier for Ingo to answer all the questions. All right, so who would like to go first? Felix Mutzel.
Hi, can you hear me? Okay, perfect.
Yes.
Hi, Ingo. Thanks a lot for the presentation. It was super interesting. I have one question on the autoencoder example. So you mentioned the dimensionality problem. Have you tried reducing the feature space, for example, with PCA, or also filtering out only those signals that are actually, say, relevant for you to tackle that problem?
That's actually an awesome question. So I need to sort my mind because I have a lot of answers on that.
Take your time.
When I start using an autoencoder, do you see me actually? I'm still struggling with the camera.
Yeah, I see you. I hope you can see me as well. Hi.
So I need to find the slide again. So if you look at this model, what it does, it basically takes the revolution speed and tries to predict the current. So if I have an autoencoder and feed in revolution speed and current and try to predict the revolution speed and current. So this is, in a sense, what the original model I described, it's called a residual model, is in a sense extremely close to an autoencoder, because I try to have some input and try to predict some output and measure the difference between input and output. On the autoencoder, I just use all data. So the message here is basically, it's not directly using an autoencoder or a deep neural network, which is wrong. You just need to think about a cause and effect behavior. So if you incorporate the cause and effect in the model, you are able to reduce the situation a lot for the model, and you also make the learning problem much easier for the model. You asked about PCA. There's one very interesting recommendation I can basically give everybody. So if you look at PCA, PCA is a dimensionality reduction, as you mentioned before. So what I can do to do the predictive maintenance task is I use the PCA to encode the data in a low dimensional representation. And then I could use the decoder of the PCA and put that back up into a high dimensional representation. So what I basically have then with PCA is a one-dimensional autoencoder. If you look extremely carefully at the deep neural network I have here, if you remove all activation functions or all nonlinear activation functions, your deep neural network is exactly a PCA. The training is a little bit. So on that part, the PCA will not help a lot, because it basically means you do the dimensionality reduction before and you still are stuck with the original input space dimensionality. I think it doesn't help too much. I don't have anything I would call formal evidence. They're trying it out in depth, but basically the first layer of your deep neural network can resemble, on the line of argument I had before, the PCA. So it should actually, if that would come to a rescue, figure that out by itself.
Okay.
Yeah. So the core message is really, if you just think about what is actually the domain. So I have a certain failure, which is the blocking of the spindle based on the aggressive dust, and this cause-effect behavior, then you can use inside actually every model you would like to do.
All right, so you suggest that, say, going with more of a physical model actually solved your problem better?
Yeah, so basically every background knowledge you put into your model reduces the amount of data you need. Yeah. So also the solution to the curse of dimensionality is you use more data. So when we go now incorporate the physical understanding, we reduce the amount of data, and that's all.
Yeah. All right, cool. Thanks a lot.
All right, thank you for this awesome question. There's another one incoming. Peter Michael Düppenbecker, the stage is yours.
Yeah, good afternoon, thanks. I really like the example with the X-ray machine, that you can sort out the pieces that you don't have to scan. What I was just wondering, how does such a system behave in the long term, and how do we as Siemens or the customer then handle this?
Sorry, can you repeat? System, I missed that part. I need to admit.
So how does the system behave in the long term? Is it stable, or do you have to?
Which example were you referring to? That was
the X-ray, the example with the X-ray machine, that you sort out the pieces that you don't have to scan.
I was not involved in that specific use case, so I don't know the details there, whether it's stable or not. The problem is, again, so if you have two production lines which are extremely similar and you stay producing the same thing, then everything is fine. As soon as you start to have variation in your data which was not contained in your training data, you might run into a problem. So now the tricky part is, I said, if you have variation in your data you don't have in your training data. So now you were mentioning the example of a different factory, a different plant, and so on. There is some variation. The thing which is always hard to tell up front is whether the variation will impact the model performance. And
so who would have the responsibility to monitor that? Is this something that we provide as a service, or is this something where the customer would have to build up this competence to monitor that? So
that is a great question. The monitoring, actually, the example was done by our customer service. Siemens, I guess. So for the Siemens people, I see the org code, but I don't see yours. So I guess you are Siemens. So
I'm from the Siemens Falcon, yes.
Okay. In that case, the use case was implemented by DE FRCS. It's one of our MindSphere applications centers. So it's our customer service, which helps our customers to realize AI applications. And one of their biggest USP is actually that they are offering to operate the model in the field, which then also includes monitoring. And I think for many customers, doing the monitoring and the operations is a big benefit we can provide, especially in the world of Siemens factory automation, but similarly for health engineers. If you look for the large companies in FA, DI, it is the automotive. In the health engineers world, it's the hospitals. They might have IT departments. But I had after a skiing accident, I have an operation somewhere in St. Anton. Basically, it was a small hospital. They had one MR device, and it was monitored, I think, from Erlangen. And the reason why it was monitored and serviced from Erlangen is that they don't have the capacity. So I think we should provide the monitoring functionality not only for our equipment, but also for this IT-like functionality for our customers.
Yeah, thanks. Great.
All right. Are there any other questions? Don't be shy. Just raise your hand. All right. I think then, yeah, we come to an end. I have one more request for you all. My colleague Katja will post a link of our feedback tool in the chat here in Microsoft Teams. And we would highly appreciate if you can give us a feedback regarding this know-how event so we can always improve ourselves. So yeah, Ingo, thank you again. It was lovely to have you here, and yeah, for your sharing your expertise. And yeah, I think we learned a lot today. So thank you, and have a nice day or evening.